Okay, so this is chemical equilibrium. Uh, so first we will be doing 100 questions because those are in the foundation builder, and then we move to the level exercises. So let's start. Question number one for the equilibrium. This equilibrium. What's this? K B, I think. No, K3. So this is the equilibrium constant third. Using the above equilibria is. Okay. So no concentration, nothing. Oh, it's pretty easy. So it's like just you are adding these two, right? Because actually, first of all, you should invert this. So for this guy, C6H5 COH plus H2O giving what? Like it's actually instead of writing all of this, I'll just write BH. No, not BH. AH. Where yeah, this probably should work. Plus H2O. This gives A minus. So here A is the yeah C6H5CO minus. That thing is A minus over here. And plus H3O plus. Okay. And for this guy, you have the reaction question. Sorry, the equilibrium constant K1. And the next thing is this thing. So it's AH plus OH minus, giving same thing A minus, but now H2O. So this thing has K2, right? So if I subtract these two reactions, and by subtracting, okay, so instead of doing that, let's just do the correct way. So what that means is like concentration of A minus, concentration of H3O plus, or instead of writing H3O plus, we just write H2O. So we'll just say this thing is H plus, right? So yeah, H plus, because in the end concentration of H2O, that's kind of that's yeah, like kind of a constant thing, so you don't have to worry. Actually, okay, you know what, if they want us to consider the concentration of H2O in that as well, we'll consider it. So it's H3O plus once again. So then you have concentration of H3O plus, concentration of A minus upon concentration of AH, concentration of H2O. That thing is K1. Similarly, K2, for that you can write concentration of A minus, concentration of H2O, yeah, all of that stuff, you know the deal. OH minus and whatever, and then divide these two equations, right? These two will be true at the equilibrium. So when you divide these two, you will see that this cancels, cool, and then this becomes concentration of H2O squared. This goes on the top, so it's concentration of OH minus and like what's this thing? This thing is AH. Well, that cancels as well. OH minus H3O plus. Right, and that thing is just K1 upon K2. So what reaction? This reaction, yeah, that exactly. That has K1 upon K2 as the equilibrium constant. So there we go. What's K1 upon K2? And from now on, I won't be explaining all of this in detail. I'll just say subtract the reactions or add the reactions, and you would understand what you have to do. Write it like those equilibrium constant equations, and then subtract with the proper scaling, right? What are we doing? Yeah, K1 upon K2, and these things are the same. So it's just 10 power negative 6 upon 10 power 9. Sorry, it's negative 5, I think. 10 power negative 5 upon 10 power 9, which is 10 power negative 14. So it should be this thing B, I think. So this is going to be B. Okay, question number 2. Right, this is B. Question number 2 is the rate of the elementary reaction given by this thing. Okay, the rate of decomposition of gaseous Hi to H2O and I2. Okay, fine. Equilibrium constant for half H2. Okay, I understand what's happening. So rate of this reaction is given by this thing, and by rate you just mean the rate of decomposition of the rate of reduction of H2 and I2, right? And that's like 2 times the rate of increase in HI. So when you divide this whole reaction by 2, you will divide this thing by 2 as well. So for this forward reaction, H2 plus half H2 plus half I2 gives what? HI. For this reaction, the rate constant is the rate is, it's gonna be 0. It's like 16, that's 8. 0.85 into 10 power negative 8 times concentration of H2, concentration of I2. Yeah, isn't that correct? Right, that's what the rate should be like. And similarly, the rate of decomposition of gases, HI. So for this reaction, so here the rate of decomposition is the same thing as the rate of reaction, because rate of reaction of HI, right? So this thing is 2.4 into 10 power negative 21 concentration of HI squared. So the equilibrium constant for this reaction is, right, so for this reaction, actually the equilibrium constant should be concentration of HI upon square root of concentration of H2 and I2, right? And when we have equilibrium, these two rates will be equal, right? So backward and forward reaction are equal, and that means this thing is like the square of that, at least. That's basically this upon that. Yes, which what would that be? This thing 0.85 was initially 1.7 upon 2, right? So 1.7 upon 2 into 2.4, and then 10 power negative 8. Where is it? Negative 18. So another one has 10 power negative 21. So 10 power negative 18 upon 10 power negative 21. That's 10 power 3. Right, and 1.7, that's a bad value. 2.4, oh, that is, no, that's not twice of that. So yeah, now what? It's like 1.7 upon 4.8. 67 over 10. 4.8. So 1.7 times 3, that would be 51, which is near to this. So it's approximately 1/3, so like 0.33 into 10 power 3. So like 330, near to that. And the nearest to that is just option B. So this is also B, hopefully. Right, we don't need all of this. Question number 3. Question number 3 is for this reaction. Okay, you given the equilibrium constant, hence K3 of this reaction. This is like it's NH4 plus, this gives NH4, so inverse of that reaction, and that's why you're dividing by K1, right? And this reaction goes on the front because you have this OH minus over there and there's no other OH minus species. So yeah, this reaction is going forward, the first reaction is going backward, and that's why K2 upon K1, which is, so K2 is like 10 power negative 14, and K1 is 5.56 into 10 power negative 10. It's like 10 power negative 4 upon all of this thing. I'm gonna approximate this as 0.5. So like this will be, sorry, no, just 5. So it's like 0.2 into 10 power negative 4, right? Yeah, which would be like 2 into 10 power negative 5. That's, yeah, I think B is correct. Right, so it's slightly bigger than 5, and that's why you have something that's slightly less than 2. So B is correct. Question number 4. For the following equilibrium, Kp is found to be, so Kp is just the pressure reaction quotient, and Kc is the concentration reaction quotient, and for ideal gases you have P equal to N by VRT, and that's why you're like, okay, for this reaction, what are we doing? So our Kp, that will be concentration of NO2 squared upon concentration of N2O4, right? And okay, I should write pressure because pressure quotient, right? That thing is Kp, and we can write this thing as like P is proportional to N upon V, which is just the concentration basically. So it's like CRT. So this is RT square, right? This involves RT square, and this thing involves RT. So RT square upon RT, that's just RT. So this will be Kc times RT, right? So it's like concentration of NO2 squared upon concentration of N2O4 times RT. I should say RT squared upon RT. That would be a better way to view it. So essentially what this is just RT to the power of delta N gaseous. What does delta N gaseous really mean? It just means the number of, like, the increase in gaseous moles per mole of the reaction happening, if that makes sense, right? And yeah, you can see how that works. It's pretty easy to prove. I'm not gonna go into that. Question number 4 is done. Wait, no, question number 3 is done. Question number 4 is, so yeah, like Kp upon Kc is just Re, and what are they saying? Kp is found to be equal to Kc, and of course this makes no sense when you talk about it with the unit, so you should talk about the thermodynamic constants for that. And for the thermodynamic constants, we will be dividing each pressure that we have by 1 atmosphere and then putting that into the equilibrium equation. And similarly, for each concentration, we'll divide it by 1 molar. Yeah, and then this would work out. So here RT, we just put that in proper units. So R is, I think it's like 8.3 joule per Kelvin per mole, something like that. Is that what it was? But you just want in terms of atmosphere and stuff, so I think it's like 0.08 something, like 3. Yeah, I don't remember how it was. Still, we can just convert this thing into whatever we want, right? So PV upon NT, that is atmosphere volume, that needs to be in liter, upon N, or I can just say N upon V, we'll just call that molar, and T, Kelvin, right? So you want to convert this thing into that. This is already there, so no need for that conversion. And this thing is just mole per liter, right? So mole, and then that's liter over here. So atmosphere liter, that's like in SI units, atmosphere is like 10 power negative 5, and liter, that is decimeter cube, that will be 10 power negative 3. It should be plus 5, sorry. So it's like 10 power 2. Yeah, this thing is just 10 power 2 times whatever is in SI units. So this thing is 10 power negative 2 times this unit. That's why we'll have 0. So just shift 2 decimal places, right? Come on, delete all of this. Shifting 2 decimal places, it's like 0.0823, whatever that thing is. Depends on what value you take it. And times temperature, right, in SI units. So, or like, sorry, not SI units, the unit thing that we are working with. What is the temperature? Oh, okay, we want to find that. So this thing is 1. So T is just 1 upon 0.083 in kelvins, of course. Yeah, like I should say T upon Kelvin. That would make more sense. But you get it. What is this value? It's like 1000 upon 83, which I don't know how to calculate. It's like 1000 upon 83. You would have 1. Just do it. That would be 7 and 1. So 170, that is well, maybe like 2. So minus 16 and 6. Yes. So 12. That's very near to it. So I'm going to go with B. Delete all of this and I'm going to go with B. Question number 5. For the following gaseous equilibria X, Y, Z are. Why is this? Is this even recording? No idea. Maybe it is. Who knows? Okay. Question number 5. For the following gaseous equilibria, ratio of Kp and Kc in the increasing order. Oh, okay. So RT is generally bigger than 1. At 300 Kelvin, yeah, then it's bigger than 1, because 300 times 0.08 something, like 3 maybe. That would be 8.3 into 3, which is of course bigger than 1. So RT is bigger than 1, then you can do some stuff, right? So talk about RT to the power of delta n gaseous, right? That's what we have as Kp upon Kc. And as RT is bigger than 1 over here, this is an increasing function in delta n gaseous. So basically they're saying just find the order of delta n gaseous. So over here you have 2 plus 1, 3, that goes to 2. So it's a minus 1. So x has minus 1, y has, right, x has delta n gaseous is minus 1, which is not good. Y has 1 and z has 0. Okay. So this would, and what do you want? You want the increasing orders. So the x, z, y, right? So x is less than z is less than y, which is C. So we'll go with C. Question number 6. Hydrogen is produced industrially by the steam hydrocarbon reforming, okay, reaction, forming process as given by this reaction. Okay. If Kc is given, what is the value of Kp at the same temperature? Come on. Seriously, you can do better than that. Okay, so all of these are gaseous, so you don't have to worry about that. The only thing I'm worried about is, oh, so it's the gaseous, right? Question number 5, all of these will be gaseous because it's given its gaseous equilibria, right? There's no solids or liquids involved, hopefully. Okay, so for question number 6, for this reaction, if Kc is given, what is the value of Kp? So just find delta n gaseous, which is, so it's like 1 plus 1 minus 1, so it's minus, sorry, 1 minus 1 plus 1, so it's minus 1, right? So Kp will just be Kc times RT to the power of -1, so like upon RT. And at temperature what? At 1000 Kelvin. Okay, what is Kc? Kc is just 3.8 into 10 power -3 upon 1000 into 0.083. That would just be 83, I think. How is this related to that? Oh wait, okay, I see what, like this times 4, no, because 3 times 4 will give us 12, that's not what we want. If this was 2, 82, then that would be 40 or something, so it's very close to 1 upon 4, I mean, okay, 38 into 10 power -4, now this thing is close to 1 upon 4, so it's like 0.25 into 10 power -4, that is something like, something around 2 into 10 power -5. Huh. Isn't that how it should be though? It's R to the power of -1 and it's 10 power -3, and does this make any sense? Right, we've been given Kc. What is the value of Kp at the same temperature? Just 1000 times R and all of that. It should be something like that. Why are all of these not in 10 power -5 and stuff? It should be like a very small number. Why is this? Is this? Oh no. Okay, I see what. This is not. This is not balanced. Sorry. You had this 3H2 over here. That's the problem. I have found delta n gaseous to be wrong. So 1 plus 1, that's 2, and here it's got 1 plus 3, 4. So 2 to 4, it's difference of 2. So it should technically be, yeah, it should be. And what I did was wrong basically. 3.8 into 10 power -3 times RT to the power of 2. And what is RT over here? It's just 8, 3 in like that thing squared. Yeah. So this will be 38 into 10 power -4 into 83 squared. What is 83 squared? 83. It's like 9 and 24 and 0. 4, 2 carried on 64 and 66. Yeah, it's like 9, 8, 8, 6. So 6889 times 38 into 10 power -4, which we can write as like 6.889 into 38 into 3.8, right? Yeah, that's a better way to do it. I think. Okay, and this is like approximately 7 into 4. Something less than that, yes, but 7 times 4 is 28. Something less than 28. Oh no, all of these things are less than 28. This is definitely wrong. 9.8 is wrong. 22 point, I don't know, like, and it's bigger than 6 times 3, which would be 24. So between 24 and 28, there's only one thing, 25.61, whatever this thing is. So B. Question number 7. For the following equilibrium, Kc is given, hence ratio of molar concentration of H2 and H2O. Ratio of molar concentration of H2 and H2O. Oh, so this thing is solid and this is also solid. Ah, I understand what's happening. So it's just like concentration of H2 cube upon concentration of what, H2O? Right, H2O cube. That thing is Kc. So I just take the cube root of that. Cool. And why do we do that? Why don't we take solid over here? Because its activity coefficient is like, sorry, its activity is kind of a constant. So you ignore that in your equilibrium constant, right? So just take that to be 1. Even though we technically just don't know what the activity is, but we ignore it and just take the ratio of H2 and H2O in consideration. And that's what we define as the equilibrium constant. So yeah. Right, so it's a myth that solids have activity being 1. No, we define the equilibrium constant differently. We don't know what activity solids have. We do know that that's a constant. And what we mean by activity of solids, we don't know that as well. Yeah, you get the idea. So what's the thing? Concentration of H2 upon H2O, that's what we want, right? That is the cube root of Kc, which is 3, so it's A. Question number 8. Which one of the following statements is incorrect? Reversible reactions do not proceed to completion. Yes, they don't. Right, A is correct. Irreversible reactions do not proceed, but they do proceed to completion. Both proceed to come. No, neither. Okay, A is correct. Question number 9. A reversible reaction is said to have attained equilibrium when the backward reaction stops. No. Both backward and forward stop. No, none of them stop. They just have it like have equal speeds. So C is correct. So D is definitely just wrong. Because like concentrations being equal. No, not necessary. In the chemical reaction, at equilibrium point, state whether at equilibrium point state whether okay, fine. Right, so it's like 1 plus C. Okay, fine. Equal volumes of N2 and H2 are reacting. No, not at all. Equal masses of N2 H2. No, the reaction is stopped. No. Same amount of ammonia is formed as decomposed into, yes. So D is correct. Question number 10, D. Why am I writing this? D. Question number 11. For this reaction, if active mass of A is kept constant and active mass of B is tripled, the rate of reaction will become. So it's an irreversible reaction. That's what they're saying. Okay. But this is more like a kinetics question, not an equilibrium question, but whatever. So if active mass of A is kept constant and active mass of B is, okay, whatever. And why do these spam? Okay. Continue. So A is kept constant. Why do you even do that? No need to say that. Active mass of B is tripled. So yeah, it's got 2B over there. That's why it will become 9 times, I think. Right, if this reaction is actually like single step, then it will be 9 times. According to law of mass action, the rate of reaction is directly proportional to molarities of the reactants. No, like mole fraction of reactants. The rate of reaction, normalities of the reaction. Does that even make a difference? All of these are just ways to represent the concentration. You can take any of these. It doesn't matter. Even though we generally take molarities, but like all of these actually work. At times you'll be taking mole fractions into account. At times you will be taking mass upon surface area, whatever that, I mean, like, okay, for surface chemistry you take that. Yeah, it could be anything, right? You take pressure as a like representation of activity, then you can take anything, right? You can take mass, you can take molarity, whatever concentration term that you want, right? So the rate of reaction proportional to, but yeah, like for like beginner level, you could say it's molarities because that's what we generally do. So A. But then for the whole complete thing, there should also be that we should take the stoichiometric coefficients into account and stuff. So this is just a bad question. But yeah, next question. What will be the equilibrium constant at something temperature for this reaction if its value for the reaction, okay, at 7.7 is what? Oh, okay. So for this reaction, you gave equilibrium constant 64. For this reaction, you just half of. No, actually half, but then the inverse because the opposite reaction is happening. So 1 upon 64, that would be for 2H2, sorry, 2HI giving H2 plus I2, and half of that reaction, that's why square root of 1 upon 64, that's 1 upon 8. That's D. Question number 13D. Question number 14. For which one of the following reactions value of equilibrium constant depends upon the units of concentration? Okay. Uh, Units of concentration. I don't understand what you. Okay, whatever. So for the first guy, like, yeah, it actually does depend on the unit of concentration, right? Because yeah, like changing the unit of concentration will change the whole scenario, right? Because we divide by that unit or whatever you set initial, like, you understand what I'm saying. How do I express what I want to say? You set some kind of initial concentration, and then you divide the actual concentration by that concentration to find the activity to be put into the equilibrium constant equation, and that's why that unit actually it matters. Yes, by unit they should probably say that initial concentration, but they are not that advanced, so just say unit. So it does. First reaction does. Second reaction it doesn't because yeah, the units just cancel up, right? I mean, you divide by the same thing, and then that same thing cancels up. So it's just the it's just this thing. It's just concentration of, actually no, pressure of N2, pressure of O2, right? Square root of that upon pressure of NO, and not pressure of N2 upon P naught, whatever P naught is, times pressure of O2 upon P naught. I mean, it is also that, but you see that this P naught thing just cancels away, right? That's what the actual equilibrium constant should be, but we treat it like that because this cancels. And in general too, we just treat an equilibrium constant like this because we take this P naught to be 1 in some unit. We take this to be 1. But seriously, man, they should just change how they are teaching this. It's such a small thing. Why don't they say it out loud? Right. So where was the question number 14? Oh, sorry, I did question number 14 in that. Sorry, 15 in that case. So question number 15. That's what I did. No, wait. That's not what I was doing. What was I doing? No, I was doing question 14, but both are looking same. That's why. Uh, right. So first reaction, no. Second reaction, yes. Third reaction, it's all solid. Actually, yes. C also looks like that. Yeah. Wait. Depend upon. Okay, so in B they don't depend. So you just want the one where it does depend. So it's gonna be A, because in B and C both they don't depend. So probably in D also. Yes, in D also, it's all just liquid. So you will be dealing with mole fraction and stuff, right? Yeah, when you go for liquids and solutions, you will see you will be having the mole fraction for the activity. So that thing, like question number 12, it was just complete bullshit. Right, question number 15. Which of the following reactions the equilibrium constant will have no units? Same thing. Look, equilibrium constant by default does not have units, right? It's just that these people treat it like it has units. Yeah, you can treat it like it doesn't. It doesn't make a difference as long as you understand that what is going on. So, yeah, the first guy doesn't have units. The second guy also doesn't have any units. The third guy, okay, so it's all of these. Question number 16. The unit of equilibrium constant for the reversible reaction, it's nothing, it's not there. So D, right? Yeah, and not like actually, but also the way they want it is that there is no unit. For a hypothetical reaction, 4A plus 5B gives this thing, the equilibrium constant Kc has units. Uh, so what are A, B, P, and Q? What are their activities? We don't know anything about it. How can you just expect us to do this? Okay, I'll just assume all of these are just in aqueous phase, right? And then their concentrations are their activities. So the equilibrium constant has units. So yeah, it's unitless because 4 plus, no wait, it's 4 plus 5, that's 9. This is 4 plus 6 is 10. So it's not unitless. So there's a difference of 1. And that's what's gonna be 1 molar. So question number 17, it has units of mole per liter, which is 8. Question number 18. For this reaction, the units of Kp will be, so it's unitless once again. Why are these? So just two, oh wait, no, it's not unitless because it's got 3H2 over there. I didn't see that 3. Right, so 3 plus 1 is 4, and then that minus 2 is 2, so it's gonna be atmosphere squared. Or pressure squared, right? Depending on how you do it. The equilibrium constant for this reaction, H2 plus I2 gives 2Hi at 700 Kelvin is 56. It's 0.5 mole of hydrogen and blue give added to the system at equilibrium. The value of equilibrium constant will be. It's the same, man. Equilibrium constant doesn't depend on concentration, it just depends on the temperature, right? So it's still 56. C. Question number 20. 1 mole of N2 and 3 moles of H2 are mixed, sorry, what? Are taken in a closed vessel of 5-liter capacity and suitable conditions are provided. When the equilibrium is reached, it is found that 0.6 mole of H2 is used up. The equilibrium constant of NH3 is. Okay, so what? N2 and H2? Right. So 2 moles of N2 and 1 mole of H2, and you don't have any NH3 right now, are taken in a closed vessel and suitable conditions provided. When the equilibrium is reached, it's found that 0.6 moles of H2 is used up. So that means just 0.4 are remaining. And the reaction is basically just N2 plus 3 H2 gives NH, I mean like 2 NH3, right? So since 0.6 were used up, like yeah, that would mean that 0.2 moles of N2 must have been used up. For every 1 mole of N2, you need 3 moles of H2. That's why 0.2 moles of N2 is used up. That would be 1.8 then. And 0.4 moles of NH3 were provided now. So it's going to be 0.4 because here's the 2 over here. Right, question number what? Question number 20. Okay, that's good. And then the total, is this 19? Yeah, question number 20. Okay. Then the total number of moles of gas at equilibrium. Wait, no, I think I am going somewhere else. Right, this thing. Question number 19 is. Oh, it should have been question number 19. Wait, what? Question number 18 was. I think I messed up some, like numbering is wrong somewhere. Question number 19. That was C. Question number, yeah, like 19 was pretty much that, and 20 was this thing. Okay, I was reading 21. I should maybe just mark where I'm going by this. I don't know. 50% N2 is converted to. Something's weird. I was doing question number 21. That's the problem. Right. So this thing that I'm doing is now question number 21. Yeah. I'm just going to continue doing it and then go to question number 20. Okay, so equivalent concentration of NH3 is, seriously, initially you didn't have any NH3, so now I just have 0.4. It's not even involving constants or whatever. Why you put this way? So it's A. Question number 21 is A. What's question number 20? 1 mole of N2 okay. Oh wait, here you have 2 moles of N2. Okay, then this was wrong because we took 1 mole of N2. Why is this so confusing? Okay, let's do question number 20 now. 50% N2 is converted to ammonia by this reaction, then the total number of moles of gas at equilibrium is. So once again, N2H2, just have 1 mole of N2 and 3 moles of H2 are mixed in a liter flask. If 50% N2 is, and you have no NH3, alright. 50% N2 is converted to ammonia, so 50% is just gone, and that's why I just have 0.5 over here, and it's like the reaction is 1 N2 plus 3 H2 gives 2 NH3, so it would have been 1. That's what it will be. And for 0.5 N2, you just need 1.5 H2. So it's like this is 1.5. Cool. So now what do you want? Total number of moles of gas at equilibrium. That's not a big deal. So it's just 3. Yeah. So question number 20 is B. Question number 21. Question number 21 is, so the same thing, N2H2, NH3. So 2 moles of N2, 2 moles of H2 are taken in a closed vessel of 5 liter capacity. We don't care about it. Suitable conditions are provided when the equilibrium is reached. It is found that 0.6 moles of H2 are used up. So that means it's now 1.4, and this would be 1/3 of that. So it's like 0.2 moles of N2 are used up, so it's 1.8. And 2 times of that's like 0.4. So now you have 0.4 NH3. The equivalent concentration of NH3, it's just 0.4, right? So it's A. Hey, it's still A. Yeah, like, okay. Question number 22. Select the reaction for which the equivalent constant is written as, okay. So K is just mx squared upon mx3 squared upon mx2 squared x2. Alright, so mx3 squared, we'll look for that. Yeah, so C is the answer. This was very easy. Why did they put this? Okay, next. The change in pressure will not affect the equilibrium constant for this guy. It does affect it, right? Because, yeah, like change in total pressure, that's what they mean. So how do I explain to you what I want to say? Like when you increase the pressure, suddenly your Kc is still the same. Sorry, your Qc, I should say, like the reaction quotient in terms of concentration, that's still the same, but your reaction quotient in terms of pressure is now different, right? And the reaction quotient in terms of pressure, that's what actually matters, right? So for reactions which have delta N gas is equal to 0, there's no effect in the reaction quotient in terms of pressure. But when there is inconsistency, like that thing, so over here, as you can see, if you increase pressure, it's gonna shift to the right side because it wants less moles. It wants to decrease its pressure. Le-Charte's principle, that's what they say. So yeah, and that's why it will shift to the right for reaction A. Similarly, for this reaction, it will shift to the left, and for this reaction, it won't shift because both have equal number of moles on LHS and RHS. So C is how it should be, right? And in fact, later on, we'll also derive, like, I'll tell you how the total pressure actually affects everything. So we'll do that later. But right now, it's just Le Chatter's principle probably. So question number 23, C. Okay, there are 50% dimer formation of benzoic acid in benzene solution. Hence, abnormal molecular weight of benzoic acid. Wait, what? Oh, okay, 50% dimer formation. Fine, fine, fine. 50% of the benzoic acid just converts to dimers. That's what they're saying. Is that what they're saying, or are they saying like the final reaction mixture that contains 50% dimer by moles and 50%? No, if we were to do that, we would do it by weight, maybe, right? Like weight moles, we have different ways to doing it. So, what are they talking about? I think they're talking about 50% of benzoic acid converting into dimer, right? Okay, okay. Hence, abnormal molecular weight of benzoic acid. I don't understand, like, why do you want theoretical values 1 to 2 gram per mole? Uh, why would that even matter? I mean, what happens when it converts to dimer? Does that weight decrease of the whole reaction stream? No, right? And you still consider the same. Oh, okay. So the total number of moles, those decreased. So that's why you're seeing abnormal molecular weight, because moles decreased, weight still remains same. So now, like, say if at the start you had some N0 moles, then half of this was unreacted and half of this, like, moles were converted to dimers. So now this thing actually becomes 1/4 of N0, right? And that's why it's just 3/4 N0. Right now, like, you go from N0 to 3/4 N0, and that's why your molecular weight increases by 4/3. So 4/3 of 122, that's 4 into, oh, that's gonna be bad. It's 488 upon 3, which is 162 something. So C probably. Question number 24, C. Question number 25. In the dissociation of N2O4 into NO2, 1 plus X varies with pressure. What is X? Oh, X is degree of dissociation, and D and D are final and initial vapor densities. Okay. Wait, what? Initial and final vapor densities. So then this thing is just a constant, because by final you just need an equilibrium. And that's gonna be constant because it's just start from pure N2O4. So yeah. And X is just degree of dissociation. So it should, like, be a constant thing, because no, okay, so I think by final you don't need an equilibrium, but when you have X degree of dissociation, that's probably what they mean. Okay, so what are we talking about? Vapor densities. Vapor densities is just the actual, like, molecular mass of that vapor divided by the molecular mass of H2, if all of that was just converted to H2, right? I mean, the same volume, the same pressure, and same temperature. If you just put H2 into the same container, then the molecular mass of that H2, the ratio of those two. So it's kind of a weird quantity. I don't know why these people use it, but they do. And so basically it's just the actual molecular mass upon 2, because molecular mass of H2 is always 2. So yeah, like, vapor densities is actually the ratio of densities. So the density of the gas upon the density of H2 if it was filled in the same container at the same pressure, temperature, volume. And it can be shown to be just the molecular mass upon 2. So that's all we need to know. right? And how do you find out? It's like capital D by D is more like capital M upon M. So just the final molecular mass upon initial molecular mass, right? So the initial molecular mass is the just the molecular mass of N2O4, and the final molecular mass. So when you have 1 plus x, wait, what? 1 plus x varies with, okay, fine. So x is degree of dissociation, and we want how it varies with 1 plus x. Okay, fine. So x degree of dissociation just have N2O4. Initially, it was at some number of moles, say n naught. Then after x degree of dissociation is like n naught divided by x, and NO2. Now that's like 2 n naught x. So these combined would just be n naught into 1 plus x, and that's why they chose this 1 plus x thing. Yeah. So now the total number of moles have increased by 1 plus x, and that's why the molecular mass will be decreased by 1 plus x, right? So this thing, capital M upon small m, that's just 1 upon 1 plus x. So yeah, it's more like y equal to 1 upon this quantity, the x variable, I mean the variable on the x-axis, not 1 plus x, that's the different thing. So that makes sense. It's just a hyperbola, C. Right. Next, number 26. In the above question, 2, whatever, x varies with capital D upon small d according to, okay, so you've got how 1 plus x varies. How does x vary with capital D? So capital D upon small d, we'll just call that y. So y times 1 plus x is a constant, say something like c. Yeah. And now I just want to figure out how is x related to y. So it's like x is c upon y minus 1. So it's kind of like a hyperbola and stuff, except that, or you can say like y into x minus, x plus 1. So yeah, that would probably make sense. Equal to 0. So it's more like a shifted hyperbola. Yeah. That makes sense. It's like a shifted hyperbola, I think. So when your x is 0, y is some positive constant, right? And you just want to figure out how y varies with that. So sorry, how x varies with that. So when your d by d is some kind of constant, x will be 0. That's portrayed in B, I think. Only in B, in fact. Wait, what? But that should be like some kind of hyperbola. So no, then it's still a hyperbola, then it should be C probably. All of these graphs are just not good because, yeah, like what is this? Seriously. This doesn't make any sense, right? If it was small d upon d, then it would have been linear, but all of these linear graphs, they make no sense because we know it's like a hyperbola. So I'm just going to assume that these were not supposed to be lines. These are supposed to be actual hyperbolas, but they are just zooming in very much, and that's why it's like this. So the graph that would make the most sense, I think, it's like when x is 0, your y, that's like capital D upon D, that should be some kind of constant. And that's why your x-intercept in the graph, that should be positive. That's only shown in C, and it should obviously be decreasing because as your y increases, your x plus 1 decreases and stuff. So your x decreases. Yeah, right. And of course, x is always like less than 1, right? It cannot be bigger than 1, right? So if I were to actually graph this, then it would be something like cutting this and something like that. So like in this region, this is the maximum x value that would be when it's 2, right? So x plus 1 would be, sorry, x would be 1, right? That's the maximum value. And yeah, it just keeps something like that, right? So this is, which graph is correct? I think C. I think C because it's the most resembling to actual graph. Okay, for the reversible reaction, net reaction is this thing. Uh, Fine. So dx upon dt. What is x? Okay, it's just the rate of the reaction. It's so yeah. This is 2.6 into 10 power negative 3. Okay, 10 power 3. Okay, fine. I get it. So the rate of the forward reaction, that is this thing, 2.6 into 10 power 3 concentration of NO2, all that stuff. And the backward reaction is 4.1 into NO2 squared. If the reaction mixture contains 0.01 moles each, okay, then the above reaction is. So just plug these values into that equation and see if it's positive or negative. 0.01, that's like 10 power negative 2, and each of N2, so NO and O2. That's like 10 power negative 2 power of 3, that's 10 power negative 6. So 2.6 into 10 power negative 3, that's the first thing, and then minus 4.1 concentration of NO2 squared, and NO2 is 0.1, so 10 power negative 2 once again, so 4.1 into 10 power negative 2. And this thing is bigger than that, so that's why this thing is negative. And this being negative, that means the forward reaction is slower than the backward reaction. So this is gonna shift to left, right? I think that's how it should be, right? This thing is being negative, then that just means it's gonna shift to the left, because is that not how it should? No, it's not shifting to the left. It's shifting to, yeah, it is in fact shifting to left. Sorry. Yeah. So concentration of reactants, those will increase. That's it. That's basically it shifting to left. So shifted in backward direction. B. 27B. Next question. Question number 28. Okay. If delta N is, what's this thing? NP minus NF. What is this thing? I don't understand what this is written. What is this, like NP minus, okay, is the change of okay, is the change in number of moles of gaseous substances. So should have just said delta N gaseous, you would have understood. Then equilibrium constant, this thing are related as. Come on. Yeah, like, why? So okay, this is wrong. Wait. Sorry. So A is definitely just wrong. Yeah. Right. So change in number of moles. So A is wrong. B is correct. In fact, yeah. So B is the thing. And then C is also wrong. D is just absolutely, like, this doesn't make any sense. It's different units, and I know I said it's unitless, but you understand that, right? It makes no sense. The ratio of Kp upon Kc for this reaction is so 1 cancels away, just negative half is delta N gaseous. So R to the power of negative 1 upon, this is D, question 29D. Okay, cool. Yes, okay. In which one of the following reactions Kp is less than Kc? Does that make sense? I think these are at room temperature. In that case, RT is a positive, like RT is bigger than 1 if it's at room temperature. So Kp being less than Kc, that just means Kp upon Kc is less than 1. So your RT to the power of delta N gaseous, that's less than 1. That's only one way for that to happen. That, like, yeah, your delta N gaseous, that should be negative. So which of these have negative delta N gaseous? So 2 becomes 3, no. 1 becomes 2, no. 4 becomes 2, yes. And D is just 0. So yeah, B is the thing. Question number 30. Question number 31. For a homogeneous chemical reaction, Kp equal to Kc when delta N is, so homogeneous chemical reaction, that just means that the moles on right side and moles on left side is 0. So That's what it means, right? No, wait. Oh, sorry. Sorry. Homogeneous just means that the phase of all reactants is the same. Yeah, that's what it means, I think. Right. So what is the reaction that has like delta and gas is equal to 0? What's that called? I don't remember it. But right, this thing happens when delta n is 0. Question number 31, 8. Right. Question number 32. A small value of equilibrium constant shows that the reaction is more in forward and less in backward direction. No, right? So like the equilibrium constant being bigger, that just means that the concentration of the final products will be large. So the reaction will be, yeah, it's like the backward reaction that's dependent on the reaction, sorry, on the concentration of reactants, and that has to be large. That means the backward reactions coefficient is smaller. Right, so reaction is more in the forward direction. Sorry, we want a small value, then that's the opposite of that. So a big equilibrium constant does that, and small does the opposite, so the reaction is less in forward direction and more in backward direction. At high temperature, no, reaction is very little forward as well as backward. No, that doesn't make sense. That would just be a slow reaction. That would not be like that. That's not related to equilibrium constant at all. At all. So B is what it should be. Question number 32. That is B. Question 33. Consider the equilibrium reactions. Just wait a second. Let me just see what time is it. It's 12:32. Yeah, we got a lot of time. It's nothing. Just like I just want to get this done in like 2 hours at least. Right? In 100 questions in 2 hours. That's what I was aiming for. Okay, question number 33. Consider the equilibrium reaction. The equilibrium constant K for the following dissociation is. Oh, okay. So H3PO4 that gives 3H plus and PO4 3 minus. So for the first dissociation you have K1, for the second you have K2, for the third you have K3, of course. Then yeah, just multiply all of them together. So it's K1, K2, K3. What's the big deal about it, huh? Right, it's just all three of them together. So it's going to be K1, K2, K3. Question number 34. And you can of course do it from the basics, like write the equations, multiply them together, and you will see that yes, K2, K1, K2, K3, that is the equilibrium constant. Okay, if K1 and K2 are the equilibrium constants of the equilibrium 1 and 2 respectively, what is the relationship between the two constants? Okay, K1, K2 are the equilibrium constants of this equilibrium and this equilibrium. What is the relationship between the two constants? What kind of relationship do you want? Oh, okay. So these are the same reactions except that this is double of that. So like K2 is just K1 squared. What are these? I mean, okay, it's foundation builder. That's why it's easy questions. But seriously, man, just give us a little harder questions. The equilibrium constant for this reaction. Zinc solid plus copper. Okay, fine. That. This reaction are K1 and K2, then the equilibrium constant for this reaction. So yeah, I just expected this. It just has that copper 2 plus gone. If you add these two reactions, that will happen because copper 2 plus copper, that whole thing will just be gone. And you will get the thing. So it's just K1 times K2. So B. And here you don't have to worry about phases and all of that because it will work out anyway. Yeah. Question number 36. For this reaction, Kc is K1. What is this? K1. Okay. And for this reaction, it's K2, the value of equilibrium constant for this reaction. Come on. Seriously. So 2AB plus B2. Okay. So you could just add both of these reactions, right? So no, that would give us a different thing. You want to get rid of what? You want to get rid of 2ab, and you also want a half b2. Okay, yes, just add both of these together. That would just be 2a plus 2b2 gives, what was it saying? Well, that 2ab gets cancelled and just have gives a to b4. So add both of these together and take half of that. So it will like square root of k1, k2. So it's c. Right, question number 36 was this thing. Yes, c. Question number 37. If fraction a of hi dissociates at equilibrium in the reaction, okay, then starting with 2 moles of hi, the total number of moles of the reactant and product at equilibrium is equal to. Come on, seriously. So it's like it starts with 2. It's gonna be 2 into 1 plus a, because it's got 1 minus a over here, and this will, okay, wait, what? It's the same thing, because yeah, like 2 goes for the left hand side is 2 moles, for right hand side also it's just 2 moles, so the change in moles is 0 overall. Total number of moles of the reactant products combined, right? That's the same thing. It's just 2. So question number 37 is C. Right. Question number 38. The following reaction was allowed to come to equilibrium. Initial amounts of reactants placed into 5-liter vessel were 1. Okay, whatever. After the reaction reached equilibrium, 1 mole of B was found. Okay, so 0.8 mole of B just went away somewhere. That means 0.4 mole of A also was reduced. Calculate the value of Kc for the section. It's like after equilibrium, right? So initially A, B, C. What were the moles? So it was 1 mole of A, 1.8 mole of B, and possibly 0 moles of C, because they didn't specify it. Okay, after the reaction reached equilibrium, right? So amounts of react, so there was no product. After the reaction reached equilibrium, 1 mole of B was found, so that means 0.8 mole of B was consumed, which means 0.4 moles of A was consumed and 0.4 moles of C were produced. That's how it should be now. Yeah, calculate the value of Kc. What kind of question is this? Question number, concentration of C, that thing, upon concentration of B squared, which is 1. So don't worry about that. Concentration of A, which is 0.6. This is 4 upon 6, which is 2 upon 3. And where is 2 upon 3 there? So 2 upon 3 is 0.06. Now that's not how it should be. 5-liter vessel. Okay, this matters now. That's bad. It's bad. So it's not just that. You also have to account for that volume, because not just the moles, it's also related to the volume. Right. So once again, the same thing. It's just 0.4 upon 0.6 into 1 squared, but instead of having this thing, you would have 0.4 upon 5, because 5 is the volume. Right, molarity, not the moles. Now this should be correct. So 1.5 square, right? This goes on the top just because 24 into 2/3. So 25 into 2/3. Which is 50 upon 3, which is 1, and we've got 20, so 6, which is 18, the 0.6, like 16.6 something, which is close to 17. So question 38 is C. Wait, no, question number 38 is, yeah, it's C, sorry. Let's do question 39 over there. Okay, so C. Now question number 39. 0.2 moles of H2 and 0.2 moles of S are sulfur, okay, are mixed in 1 liter decimeter cube is just 1 liter. Vessel at 90 degrees Celsius. So 1 liter, you don't have to worry about dividing by volume, just the moles is the molarity also. The partial pressure of H2S formed according to the reaction would be. Okay, so oh, you gave us the Kp. Fine. 0.2 moles of H2 and 2 moles of S. So sulfur is solid. You don't have to worry about its like concentration at all. The partial pressure of H2S formed according to this reaction. So notice that Kp is unitless and delta N gaseous is like 0. H2S is also a gaseous product. Yeah, so delta N gaseous is 0. That's why Kp is the same thing as Kc, right? Just a ratio. And that would mean that 6.8 into 10 power negative 2, right? That is concentration of H2S. And if initially we were starting at 0.2 mole of H2, right? And this would be like 0.2 alpha, where alpha is the degree of dissociation and stuff. And this will be 0.2 into 1 minus alpha. So now we can find what alpha is, and from that we can find the concentrations. Right. So notice that this thing is like very small, and now here some concepts of ionic equilibrium come into play. So what we will do is we will assume that alpha is very small compared to 1, and that's why we can ignore this thing altogether. Right, this thing is like 0.068, very small. So alpha being this thing like 0.07 approximately upon 1 minus alpha is like, I don't know, it's very small. So you can use the binomial theorem over here, and that would be 1 plus 0.07 and stuff. So this is like 0.07 plus. Yeah, there's no point in doing this. So 0. Like it's like 49, but upon 10,000. So a very small quantity. And that's why it doesn't actually affect this computing that much. So it's okay to say that, yeah, alpha is like approximately 0.07. Once you found that, or you approximated that, you can find everything else. So this will be used in equilibrium of like acids and bases. So in ionic equilibrium as well, right? Where you have to use this like basically a lot. The whole chapter is based on just these kind of approximations. So just get used to it, right? It's the first time you have seen this, but it will be used a lot. And actually that question wasn't, I mean, this question wasn't that bad. It was just alpha upon 1 minus alpha equal to something very small. So you could have also done this a proper way, like call this thing x, I don't know. What was this, k? Then this would be alpha equal to k minus alpha k, and then that would be alpha equal to k upon 1 plus k. But then once again, k is so small, so you can ignore this, and it will just be k. But yeah, k upon 1 plus k if you want to be exact. So that works. So alpha is approximately 0.07, and that means your H2 polarity didn't actually change all that much. What do you want? You want the partial pressure of H2S. So that would be 0.07. That's the mole. Sorry, that's the degree of dissociation. That times your initial, so 0.2. Right, that's the number of moles. And so PV equal to nRT, and that means P is N times RT upon V, and we don't know what RT upon V is, do we? Actually, we know what V is. Do we know what RT is? Yes, we know the temperature. We know also what R is. So it's not that bad. So R will be like 0.082 or 3, whatever you want, times temperature. So 90 degrees Celsius, that is 273 plus 90, that is 300 and what? 363, something like that, upon, so RT upon V. V is just 1. We don't have to worry about that. That times this N thing. So 0.07 into 0.2 into 0.08 into, what is this like? Why is this so bad? 363, right? Something like that. So 363 is approximately 400. I know I shouldn't do that, but still, just make that approximations like 400 something. So 8 times 4, that's like 32. 32 times 0.2, that would be 6.4. 6.4 times 0.07, that would be like, so 6, that's 42, 42, and 28. That is 448, which is approximately 500. But then you got 1, 2, 3, so 0.5 near to that. Okay, unfortunately, all of these things are actually 0 point, like it's near to 0.5. No, this thing is not near to 0.5. This thing is also not that near to 0.5. I think it is C that we should go with. Actually, no, it could be B or it could be C, any of these. So what did we do? Actually, we decreased the whole thing, right? So sorry, we overestimated the whole thing, because 363 to 400, that's a big leap. So actually our value must be smaller than what we are expecting. And that's why it's like, yeah, 0.38 looks good. I'm gonna go with B. Or either I just made some kind of error. That's why I didn't get a close answer. And if my theory is correct, then yeah, maybe like B is the way to go. Question number 48. Sorry, 40, not 48. For the following reactions occurring at 500 Kelvin, arrange them in the order of increasing tendency to proceed to completion. Okay, tendency to proceed to completion. Okay, I mean none of them are going to proceed to completion. We just know that, but still, like by tendency, probably mean somehow find degree of dissociation, and if it's like very big, then that's good. What do we have here? Okay, KP is this thing. Huh. So all of these are like very much similar, just that their KP are different. So how do we get a fair match between all of these? You just put 1 mole of NOCl and 1 mole of NO2 and 1 mole of SO2. Sorry, SO3. Yeah, that would be a fair fight between these. And that means like, because all of these reactions are pretty much the same reaction except just different reactants and products and different KP values, right? So your alpha is like alpha increases if your KP increases as well, right? Okay, so the biggest KP, which of them has the biggest KP? Yeah, the first reaction, right? And then you have the second reaction, and then the third reaction. No, wait, actually first, then third, because 5.9 is bigger than 1.3. So first, third, and then second. So 1, then 3, then 2C, right? 40C. Question number 41. I'm gonna do till 15, then I'm going to stop, because I fear that this might be, this might actually just stop by itself. So I'm just going to do till 15. The equilibrium constant for this reaction at 1000 Kelvin is 3.5. What would be the partial pressure of O2 with equal moles of SO2 and SO3? Oh, so SO3, SO2 are just equal. That just means equilibrium constant is 1 up, like, okay, the reaction quotient is just 1 upon concentration of O2. And this should be equal to the equilibrium constant, right? Yeah, just for this case, when SO2 and SO3 both are equal, we can write the reaction quotient like this. And what are they saying? The equilibrium constant for this reaction at some temperature is 3.5. What would be the partial pressure of O2 gas? Yeah, cool. That just means concentration of O2 is 1 upon 3.5. And that's like in atmosphere, I think. Which would be something less than 0.333. So maybe like 0.3 is the best. So A, I think, A, you can write this as 2.17 as well. It's like 2 and divided by 7. So 0.20 over there, and then it's like 3 looks very close, but then 2, so minus 14 and then 6, so that is 56, that's like 0.8. So yeah, this looks very close. So 41a, 42. A reaction takes place in two steps with equilibrium constants, this for slow step and this for fast step. The equilibrium constant of the overall reaction will be, oh wait, so equilibrium constants are there, then it doesn't make a difference if this is slow or small. So yeah, it's just 10 power negative 2 plus 2, which is 0, so 1. See, right? It doesn't matter if it's slow or fast, because in the end, at equilibrium, you will have just the equilibrium constants multiplied, right? If it was not at equilibrium, then you would have some problematic things going on, because that will be that then it would be kinetics and not equilibrium, right? Okay, question 43. Kc for this reaction is given. Number of moles of PCl3 to be introduced in some liter vessel, initially evacuated to obtain. Okay. I get it. So if initially you had concentration C of PCl3, right? What was this PCl3 or PCl5? Okay, PCl5. Right. So PCl5. Initially, say you have what's the Cl2 and PCl3 over here. So initially you had some concentration C, and then after, like this was 0 0, and then after the reaction, after equilibrium is attained, you just have C minus alpha. And yeah, it's just 1 and 1. This will be C alpha, this will be C alpha. So the reaction quotient over here is also the equilibrium constant, basically. That will be C times alpha squared upon 1 minus alpha. And this thing is equal to what? Now we are going for the reverse reaction in that case. Okay, whatever. So the reverse reaction, that would be 1 upon 15. Right, and then this upon C. That's what this quantity should be. So what do you want? You want so the number of moles of PCl5 to be reduced to obtain concentration of Cl2. Wait, what? That's very weird, because what that means is like C alpha is, okay, if that's 0.2, then this thing is just 0.2, this thing is 0.2. Oh, this is very different. So concentration of PCl5 at equilibrium we don't know, but upon 0.2 squared, right? Yeah, and that's equal to our equilibrium constant, which is just 15. And that means that goes on the top, just have PCl5 equal to what? 15 into 0.04. So like 0.2 is just 1 upon 5. So it's like 15 upon 25, which is 3 upon 5. So you got this thing, which is like 0.6. Okay, so if this was 0.2, 0.2, and 0.6, right? And that must mean this must have been 0.8. So that 0.2 molar concentration just went away from PCl5 and became Cl2 and PCl3, and this was now 0.6. So now you know what the starting concentration was. It was 0.8, and 0.8 times the volume, which is 2.5. That would be so like 1640, it is 200, I think. 200 and then 2 decimal places, like just 2. Yes, so it's C, 43C. Once again, what's time? Okay, fine. 44. Pure ammonia is placed in a vessel at temperature something where its dissociation is appreciable. At equilibrium, Kp does not change significantly with pressure. I mean, it's ammonia, so yeah, like Kp, that is a constant, because at some certain temperature, your both Kp and Kc are going to be constant. But what I was saying, what changes with pressure is the, what do you call it? With pressure. Okay, wait. I was doing something else, I think. Your N by V should not change because your Kc should be constant. No, it's R. Yeah, your Kp would probably change, in fact. It changes with temperature, not with, yeah, of course, like it doesn't change with the temperature, it changes with, sorry, it changes with temperature, it doesn't change with the pressures. So yeah, it's correct, both Kp and Kc don't change, and that's why we call them constants. Yeah, so Kp does not change, that's correct. Alpha does not change with pressure, it does change. Okay, alpha changes with pressure because Kc also changes, Kp also changes, so alpha is also changing. Sorry, with temperature, what am I saying? Yeah, sorry. Alpha does not change with pressure. No, wait. Something's wrong because N by V should be doing that and pressure should also be doing that. So if you increase your pressure, that's going to be a problem. What happens when you increase your pressure but do not increase your volume? Well, yeah, then in that case, in a particular ratio, all of the moles will be decreased so that it matches the pressure completely, or increased depending on what you did. Oh, okay. So yes, it does not change with pressure for some reason. But how can that be? Because, oh yeah, for changing pressure, you should also change the volume. That's how it should have been. You can't just change the pressure without changing the volume, right? Because PV equal to nRT. So, huh. Right. When you change the pressure, your volume will also decrease because that, yeah, it will attain a new equilibrium. And for that, your volume will decrease. If you increase pressure, your volume will decrease. And then at that new equilibrium, that will happen. Cool. Sorry. So yes, your alpha does change with pressure. So this thing is wrong. Concentration of NH3 does not change with pressure. It does change. Concentration of H2 is less than that of N2. No, I don't know about that. Pure ammonia is placed. Oh yeah, actually we do know about it. So concentration of H2 is not less than N2 because ammonia gives 3 H2 plus 1 N2. That means H2 has bigger concentration. Right. So yeah, like D is wrong, C is wrong, B is wrong, and just A is correct. Question 4A. Question number 45. In the manufacturing of H2SO4 with the following equilibrium, reaction proceeds in the forward direction if more SO2 is added or more O2 is added or SO3 is removed. So B is correct, D is incorrect, C is incorrect, A is no, it's irrelevant. It doesn't make a difference if H2 is added or removed. So B is the way to go. Variation of log base 10k with 1 upon t is shown by the following graph, in which straight line is at 45 degrees Celsius. Okay, 45 degree. Okay, hence delta H is, oh come on. So log base 10k. So you know that natural log k, I should say like natural log of k2 upon k1 is delta H, or I should say negative delta H upon r, into 1 upon T2 minus 1 upon T1, right? This reaction is called like, what is called Van Hoff equation something, whatever. It's basically some kind of approximation where you assume that delta H and delta S are constants with respect to temperature, and then you can derive this equation. But it's practically useful because a lot of times that is how it is. Changing the temperature doesn't change your delta H a lot sometimes, right? And then we can use this, of course. Okay, so what are we doing? Variation of log base 10 of k. So having natural log, you could also change this with log base 10 k2 upon k. My question is k upon k naught. Yeah. And how would you have k naught? Like some t naught value. That's how it would be. So natural log, that's log base e, which is log base 10 upon log base 10 of e, which is okay. This times natural log of e. That's gonna be approximately negative delta h upon r times natural log of 10, which is 2.3 something, 2.303 I think, and this will be 1 upon t minus 1 upon t naught. Right, so you can say that log base 10 of k is r natural log 10 into 1 upon t plus some other constant that we don't care about. So it's going to be linear, and yeah, like, so it's a straight line at 45 degrees Celsius. That means this slope is 1. So just have delta h equal to negative r. What was I doing once again? And it's with 1 upon t, so it's okay, cool. The slope is 1, that means it's just negative r natural log 10. Yeah, oh, so r in calorie, I think. So putting r in calorie per Kelvin per mole, like that, and that times natural log 10. Right, right. And over here we are not taking the units of temperature in account and stuff, so we'll just have it in calories. And yeah, so it will be 2.303 times 2 because r is 2 calorie per mole Kelvin, and that's why it is 2.3 times 2, which is 4.606. So A, I think. Oh wait, B, sorry, because it's supposed to be negative. So question number 46 is B. Right, B. So your delta H is negative. That's why when you increase your temperature, that is, you're decreasing your 1 upon T value. Yeah, when you're decreasing your 1 upon T value, that is, you're increasing your temperature, your equilibrium constant decreases, because this is an exothermic reaction. So increasing temperature is not favorable for the reaction. Question number 47. Consider the following equilibria at 300 Kelvin and 400 Kelvin with the equilibrium constants. Thus, okay, so 300 and 400, fine. So first reaction, your equilibrium constant is 10 at 300 and 400 it decreases. That means it is it's exothermic. First reaction is exothermic, second is endothermic, because in second it increases. Yes, when you increase the temperature. So second is endothermic and first is exothermic. B. Which of the following factors will change the value of equilibrium constant for the reaction between N2 and O2? Change the value of equilibrium constant by adding a catalyst doesn't change the equilibrium constant, because equilibrium constant is a thermodynamic property, right? So it's related to thermodynamics, and thermodynamics is related to the final and initial state. It's not related to the process through which we go from the final to initial state. Sorry, the initial to final state. Right, and that's why adding a catalyst doesn't change anything. It does increase or decrease the rate of both forward and backward reaction simultaneously, but it doesn't change the equilibrium constant. Increasing the pressure, increasing the temp, okay, increasing concentration of N2O2. So A and B, those also don't change anything, but C, it does change everything, as we just saw. Right. Question number 49. At a constant temperature, if a small amount of one of the products is removed, the equilibrium constant small amount of one of the products is removed. Oh, okay, products is removed. Okay, then the reaction proceeds forward. So the equilibrium constant, well, that is unaffected, but uh, your equilibrium is shifted to right. That does not mean the equilibrium constant is shifted to anything. So it remains unaffected. Question number 50. The equilibrium constant for this reaction is 64 if the volume of the container is reduced to half. So it doesn't matter because uh, this guy has delta n gas is equal to 0, or I should just say delta n is equal to 0. So this will have its reaction quotient as a unitless quantity, and that's why it doesn't matter if we change the volume because it will get cancelled anyway. The value of the wait, what? Oh, it doesn't matter. Yeah, okay, of course. So it actually doesn't matter now, because even if it was not this, say it was something else, like this was N2 plus 3H2 giving NH3, it was this reaction, then too, changing the volume does not change the equilibrium constant at all, right? That's just wrong. But for this reaction, it also doesn't change uh, the proportions. So that's a bonus thing. Okay. So it's still 64. What's the big deal? Question number 51. Or did I say I should stop at 51? Let's just stop at 60. Yeah. Two samples of HI, each of 5 grams, were taken separately in two vessels of volume 5 and 10. It is respectively at 27 degrees Celsius. That's like 300 Kelvin. Two samples of HI, each 5 grams, were taken separately in two vessels of volume something. The extent of dissociation of HI will be. Oh, so volumes are different. So same moles, but volumes are different. So in the first guy, it's, hey, it doesn't matter because the reaction is just 2HI giving H2 plus I2, right? So once again, delta N gas is 0, your reaction quotient is unitless and stuff. It doesn't matter. So it's the same. Changing your volume doesn't change anything now. It's the same in both. So C. Question number 52. Which of the following the increase of pressure favors the backward reaction? So increase of pressure favoring backward reaction, that means the products must have more moles. So A actually does do it, right? Because 2 to 3, right? D you don't include it because it's solid. Then in C you have 2 to 1, which is no, that's not cool. And then B you have, once again, it's like it's 0, so delta N gas is 0, B is unaffected, and A shifts to left, so it favors the backward reaction. By increasing the pressure you go backward. So A. For this reaction, 2 moles each of A and B were taken in a flask. The following must always be true when the system attains equilibrium. What? 2 moles each of this were attained, okay, taken in flask. The following must always be true when the system attains equilibrium. Well, of course, your concentration of A, that will be smaller than concentration of B, because from this you have remove 2x, from B you just remove 1x. So B will have 2 minus x as the final concentration, A will have 2 minus 2x as the final concentration. So yeah, concentration of B is bigger than the concentration of A. So question 53, B. The equilibrium, this equilibrium is attained by mixing equal moles of P4 and Cl2 into an evacuated vessel. Then at equilibrium, so equal moles, once again the same thing. So P4 will have more moles at equilibrium. So this will be C. You can't say anything about like PCl3 because we don't know anything about the equilibrium constant, right? We don't know for how much X will go. An equilibrium mixture for the reaction had 1 mole of hydrogen and sulfide and 0.2 moles of H2 and okay. What is this question? Why? All in 2-liter vessel. So its concentration of S2 uh, 0.8 moles of S2, okay. Then concentration of H2 squared. So 1 mole of hydrogen, it's like 1 upon 2 squared upon what? Like 1 mole of hydrogen sulfide, sorry, 0.2 moles of hydrogen. Okay, that's how it should be. Okay, 1 mole of H2S, right? It's gonna be 1 upon 2 squared. Cool. This cancels. Just have 0.8 upon, which is 0.4 times 0.2 squared, which is also 0.4. So that's like 0.16. Sorry, 0.2 squared is 0.04. This would be 0.016. Yeah. So the value of Kc is just 0.016, which is B. So 56B. Right? Yeah. Next question. For this reaction, if 1 mole of I2 is introduced into a 1 liter flask at 1000 Kelvin at equilibrium. Wait, what? For this reaction, Kc is given. 1 mole of I2 is introduced into a 1 liter flask. So 1 molar concentration basically. At 1000 Kelvin. It doesn't matter. Then at equilibrium. Oh, okay. So it's like, what will be your concentration of I? What is this? This is just, oh, it's atomizing this thing. Fine. So it's like concentration of I squared, x squared upon 1 minus x. Sorry, 1 minus 2x, I think. Because then it should also be 2x, right? So it's like 2x squared upon. Now this will be 1 minus x. Yes. Right. This thing. And Kc is this guy, 37.6 into 10 power into 6. Right. That's actually very small because, okay, so this will be like x squared and this is upon 4, which is 9.4 into 10 power negative 6. So it's pretty small. From that you can say like, okay, x squared is, so like x is very small in comparison to 1, then x squared is approximately this thing. Yeah, like 9.4 into 10 power negative 4. So negative 6. So x will be square root of 9.4 into 10 power negative 3. Square root of 9.4 is something bigger than 3. So yeah, you got it. It's like 3 into 10 power negative 3. That is in fact very small. So that's good. Where was I? Question number 57, right? At equilibrium, of course, concentration of I is very small and concentration of I2 is still very big. So A is correct. Unpredictable? No, it's not so unpredictable. It is predictable. So A. Cool. Yes, that's how it should be. Question number 58. At 448 degrees Celsius, the equilibrium constant of this reaction is this thing. If we start with this much moles of Hi, this much moles of H2, this much, okay, then at 448 degrees Celsius. So just find what the reaction quotient is. The reaction quotient would be 2Hi squared, Hi squared, which is like 2 to 10 power negative 2 squared Yeah. And look, this only cares about the moles, no volume involved in that. So we can just forget about this 2 liter vessel and focus on the moles. And you could also scale this down. So instead of having this 10 pound negative 2 mole everywhere, just have like 2 mole of HI, 1 mole of H2, 3 moles of I2. So scaling it down, just have one up in this case, because yeah. So HI, that thing squared, so 4 upon 1 into 3, that is 4 upon 3, that's bigger than 1. Not important. Okay, 4 upon 3 is this, it's actually much smaller than 50. That means your reaction should proceed forward, right? So B is the way to go. Yes. Question 59. Something moles of phosphorus pentachloride PCl5 were taken in a closed vessel and dissociated into phosphorus trichloride and chlorine at equilibrium. Total number of moles of the reactants and the products were 2.53. Okay. The degree of dissociation is fine. So it's like 2.2 times 1 plus alpha. That thing is 2.53. So 1 plus alpha is just that. Okay, then alpha times 2.2, that would be 0.33, right? So 0.33 upon 2.2, which is like point, sorry, 0.33, yes. So 3.3 upon 22, which is 3 upon, so, sorry, 0.3 upon 2, which is 0.15. That's it. That's the degree of dissociation. So C, that was, I did it orally. Man, that's nice. So 0.15, that's only C. Question number 16. Last question. The value of Kc for this reaction is this thing at certain temperature. The number of moles of O2 present at equilibrium is this. At equilibrium, fine. In a 10 liter vessel such that the active masses of, oh, okay, fine, the same kind of thing, 10 liter vessel. So just n upon 10, 1 upon that, right? Because, no, in this case, it's not 1 upon that, it's in the numerator. This is equal to 10. Seriously, what was this? So, yeah, it's just 10 moles. Sorry, 100 moles, yes. Yes, that's how it should be. So 100 moles. And what do you want? You want the number of molecules present. Well, that's different. Okay, 100 moles is going to be 100 Na molecules, but Na is Avogadro's number. So D. Okay, that's it. I'll stop now. I'll see you guys in the next video.